Hello and welcome to the Oxford SARS-CoV-2 lecture series, a webinar through which we hope to invite brilliant minds from around the world to give presentations focused on COVID-19 research that are wide-ranging and promote learning, inspiration, and innovation, and provoke conversations that will dictate the future of healthcare. My name is Barack Amala. I'll be the host for today's lecture. Before transitioning to the lecture today, I would like to briefly introduce the organization hosting the series, an upcoming webinar, and our guest speaker for today, Dr. Chandan K. I will also highlight the procedure for submitting questions for the guest speaker today that we will address following the lecture during a short Q&A session. This event series is hosted and organized by the Oxford University Personalized Medicine Society, a student and faculty-led organization that works to weigh the benefits and detriments of precision healthcare in modern-day medicine. We'd like to take this moment to thank our sponsor, the Oxford Center for Personalized Medicine, which is a partnership program between the Wellcome Center for Human Genetics and St. Anne's College, University of Oxford. Throughout the year, we collaborate to hold guest speaker events encompassing a diverse array of subject areas, interdisciplinary symposiums, and field trips for all affiliates of the university. We've had the pleasure of hosting such accomplished researchers as Dr. Adrian Hill of Oxford and Dr. Dan Baruch from Harvard University. If you're a current member of the university and would like to get involved, please register using the above displayed QR code. If you have any questions regarding the society, please email us at oxmed@ox.ac.uk. Our guest speaker for today is Dr. Chandan K, a J. Stanley Battersby Chair and Professor of Surgery and Director of the Indiana Center for Regenerative Medicine and Engineering. At IU, he serves as Associate Vice President of Research. At the IU School of Medicine, he serves as Associate Dean of Research. At Indiana University Health, Dr. K is the Executive Director of the Comprehensive Wound Center. Dr. K is recognized as a Lilly INCITE scholar, and his lab has shown the potential of an electroceutical fabric to be utilized as PPE in the fight against coronaviruses. For our upcoming webinars on Friday of this week, we will be hosting Dr. Scott Boyd, Associate Professor of Pathology and endowed faculty scholar in Allergy and Immunology at Stanford University, who will be presenting a talk entitled Human Antibody Responses to SARS-CoV-2, Personal and Public. Please sign up using the link provided on the Ox Talks page associated with our series. Finally, if you have questions for our speaker today, please submit them using the Google form provided here, and we'll present them to our speaker following the lecture. Now I'd like to hand things over to Dr. K for today's talk. Please stand by as we transition to the lecture. Thank you.
Do you see my screen, Bharat?
Yeah, I think it's still in the speaker view.
In the speaker view, okay. I'd stop share and I'll share the other screen. How about now? Please let me know.
Yeah, looks perfect.
All right, thanks Bharat, and thanks to the organizers of Oxford Talk. You know, I think you have got me on for a fun talk, and fun I say because this is not what we do sort of for a living. We are a regenerative medicine center, and we are of course interested in infection, and we were trying to find out how to manage infection as you try to repair and regenerate parts of the body, and that is what took us to infection. And while we were doing that, we stumbled across something quite interesting that applies electric forces to manage infection. And during the shelter in place, that translated to testing on how COVID virus, the SARS-CoV-2, in this case a coronavirus model organism infectivity, was tested. So I'm going to talk in broad strokes a new paradigm. And this paradigm is about the electroceutical management of pathogens. Now, electroceuticals are not new. They've been there for a while and normally used for pain management. It's used for all types of pretty much neuromuscular nerve-related applications. We all know about the pacemaker. So electroceuticals in general are not new, but the application of electroceuticals to manage infection is an emergent field. So we can hardly think of a day without electricity. Let me see if I can get my slide decks. Let me see. Oh, I guess I need to do it from here. All right. Is the slide changing on your side?
Yep, looks good.
All right, good, good. So we think of electricity in physics and engineering and many other places, but what we don't realize is if we trace the history and any discoverable history that we are talking, we would see that the first mention of electricity is as the thunderer of the Nile. And this is a very good example of what what we today know as bioelectricity. But those days, when Luigi Galvani came, as we will see in a few minutes, started calling it animal electricity. So electricity did not come to human civilization as some of the forces. It looks like it came as animal electricity, and this is obviously a distant past. And here you have organisms, more so aquatic organisms, that have electrocytes that can actually store power like tiny batteries. And guess what? Those days, way back when, according to the historical records, it seems that these types of electric eel were actually used for the management of gout and headache and whatnot. So in other words, the use of this animal electricity those days back when was still there. So this is, after all, not that novel. Now, fast forward many centuries, and we now come to one of the founding fathers of the field, and we all know about the kite experiment, the lightning rod experiment. A very long story, very short. Lightning has been, providing major insight into the fundamentals of electricity in the 17th and the 18th century. And soon after Benjamin Franklin, 1752, a few decades later, we had Luigi Galvani. And Luigi Galvani was the first to talk about animal electricity. And he was able to see that, when you had these frog legs, there's a story about him walking through a wet market, and when the lightning struck, that some of these frog legs were twitching. He then followed up with appropriate experiments, and he was able to show that with each flash of lightning, the frog's leg could twitch and jump as if they were alive. So these are some of the historical foundational experiments that tickled curiosity in the area of electrophysiology, and I would say that's the founding set of experiments in electrophysiology. Now, if you look at today, and we look at the animal kingdom, animal electricity, also called by some today as bioelectricity, is not so uncommon. It is in particular very common in the aquatic animals, where in many cases they have these electrocytes that actually generate electricity for purposes of, say, numbing their prey, so on and so forth. Then you have a separate set of animals, like you see here, the bees, the hornets, the geckos, the spiders, and they actually use static electricity. For example, the gecko uses that to climb up a vertical surface, and they use static electricity. And then there's another set of animals that are very prominent for the presence of electroreceptors. So you have here a few animals that actually uses these electric receptors to hunt and so on and so forth. So this is evolutionarily conserved, it seems, and this is not that far-fetched. And electricity and biology, in my opinion, are tucked together in many ways. Now, fast forward many, many more years, and now we come to the two types of dressings, because we are primarily interested in injury and repair of injury and regenerating tissue that got injured. So we speak in terms of dressings and how you could dress the place such that you could minimize infection. So this is a problem, a nagging problem in the field. And a few years ago, the work started at 2011, 2012, and at the time, we got in touch with the company and Vomaris Inc. And here you see to the left of your screen this textile. It is basically a very simple textile that has these dots in it. These are silver and zinc dots placed in a particular proportion and in a particular geometric pattern, such that when that particular textile is made wet by any liquid that contains electrolyte, you drive electrochemistry, and you are able to, without any other external battery in the way we know, we are able to generate these types of volts up to about 1 volt. And the question is, what is this good for? And there's a separate paper, I don't talk about it today, that we published in IEEE, demonstrating you can actually connect some of these batteries on fabric in series, and you can light a bulb or power some type of a thermometer, so on and so forth. So it's actually harvestable power. But that aside, let's come back to the point here. The interesting part is you do have very weak current flowing, but the more important part from our standpoint of therapeutic functionality is the fact that you have electric field that extends beyond the surface of this material. And because this electric field, as we see, is what that matters to manage infection, you can actually manage infection at a distance from where the source of this particular power is. Now, in this particular format, as you see to the left of your screen, the polka dot type fabric, there the electrical power clearly is not scalable. However, we then developed another one that is to the right, which is scalable. Another one to the left came from this company, Commercialization, and I, in all disclosure, I serve as a scientific consultant with the company. Now we went back to the drawing board in our laboratory and developed the one that you see to the left, to the right, and this is labeled as Roy et al. And this here, this is a 6 volt, and you can put different types of resistors in it, and you can tweak, the power that you need, the field that you need, and based on the application that you want. So here you have a tunable, if you will, to the right, where you can dose, and to the left you have something that is non-tunable. It is very simple, and both today are being used in humans and have been proven to be safe for use in humans. So way back when we were trying to see whether we can manage infection, the first order of business for us is to see do no harm to the host. So in do no harm to the host, there was a series of experiments to find out how would the host body take this, and there was a large series of experiments. I'm just sharing with you some highlights, and what we were doing was to see how the skin cells would be able to handle this type of electric field. And after doing a series of experiments, we came to the conclusion that actually at this level of weak electric field that we have, we were able to generate low levels of hydrogen peroxide within the cell, low levels at signaling levels, which then actually drove redox signaling processes. We were able to energize mitochondria, so mitochondrial metabolism went up, and we were able to affect the thiol disulfide balance within the cell. As you know, it plays a key role in protein folding and many other fundamental processes, and we were able to affect that. And in one example, we had more function of this adhesion molecule, integrin alpha V, which then also was talking to the IGF-1R phosphorylation pathway. Taken together, we were able to achieve faster keratinocyte migration, which is absolutely necessary for the closing of a skin wound in this particular example. So with that in place and other studies showing that there were no detrimental effect on the host, and the fact that the effects on the host were actually pretty positive, and that is a separate topic. I'm not covering that today because the focus here is on the pathogen. So we then turned our attention towards biofilm infections. So about 2/3 to 80% of all clinically relevant infection are in the biofilm format. So in the planktonic format, if you will, the bacteria swim in, say, bodily fluids, but in the biofilm format, they actually form aggregates. As you see to the left of the screen, marked placebo, they form aggregates, and these aggregates then start spinning EPS, or extracellular polymeric substance, and this polymeric substance, the EPS, starts encasing the aggregate in a way that this encasing deters the host immune defense system from accessing the bugs, the pathogens. On one hand, on the other hand, you have antibiotics that don't get access to the bugs. Taken together, the biofilm format of infection is a pretty formidable format of infection. And by the way, if you go to the standard of care in hospitals and they're trying to detect infection, they do that through what is known as colony forming units in our hospitals. And biofilm bugs go into quote unquote a hibernation mode where they may not be forming colonies. So in other words, biofilm infection can fly below the radar of the standard clinical detection systems. So it becomes very difficult of a problem in the clinic, especially when you're trying to manage a patient with such infection. The path results will come back as infection negative. 7 days later, unfortunately, has happened with our own patients. You have this infection be present, sepsis, death. So in this case, what you see to the left of the screen is placebo, and you see those aggregates. All you now do is don't provide any drugs to it, just provide the dressing, and the holes that you see and where it says AGZN dressing, those are the holes in the fabric itself, but you see the aggregates have been now broken. And then silver alone, silver, as you know, has antimicrobial properties, is only useful to a limited extent. The electroceutical part, which is not silver alone. And by the way, all the experiments that we have done silver alone and zinc alone as well, and have come to the conclusion that it is the silver-zinc couple in this particular case that is responsible for the action. Therefore, I share with you the results from the silver zinc and attribute those effects to the electroceutical properties of the fabric. Now, right the same year when we published that, came out this very important paper in Nature reporting that ion channels enable electrical communication in bacteria. So many of you are here biofilm experts, so please bear with me. The point I'm trying to make to the rest of you is that when these bacteria start talking to each other, it's a format of, say, social communication, if you will, between bacteria. They establish what is known as quorum sensing, and that is required for the bacteria to move into the biofilm format. And during this process, a lot of communication happens between these microbes and across species, between species, so on and so forth. This communication happens, and this communication is central to the subsequent formation of the biofilm and the aggregate. So what this paper was able to show is that indeed these microbes are reliant on electrical communication, and basically our strategy, then we put 2 and 2 together, and basically we're starting to think in the direction that if they are dependent on that communication, and now if you generate some noise, if you will, using the dressing and disrupt that communication, that's one way of disrupting the biofilm. So we came up with another paper demonstrating, so in this paper, beautifully it was shown that potassium release, the paper by Prindle et al., showed that potassium release caused these depolarization waves that actually propagated across the biofilm structure, and it resulted in the coordination of metabolic state within the biofilm. Now, the metabolic state within the biofilm is critically important. Metabolism gradually goes down, and in certain parts, and as you see in our paper that is shown below, you will see that when we took a hyper biofilm, the species that actually was in a variant, I should say, a hyper biofilm variant, here, what you can see here is that the PA01, a Pseudomonas wispef variant, showed that most of the higher metabolism bacteria are anchoring to the surface where the biofilm anchors, and the ones that are on the top have lower metabolism. So metabolism coordination is a critical part of the severity of biofilm that the microbe would make. So this was again also sort of falling in line with the literature, and this was 2015. Now, if you take these Pseudomonas bacteria, in this case, it's a PA01. So you see in the placebo, and if you can see well your screen, you have agar gel, and the bacteria is all over the place on the agar gel. But in the other one, if you have these dressing 5 millimeter below the surface of the agar where the bacteria is growing, that part of the gel will not let any bacteria grow. So clearly you see a zone of inhibition where the bacterial clearance is there. So that was very encouraging in that even at a distance, and that's how we figured that this was not current itself, that you have field, and within that field, these bacteria clearly are very uncomfortable even growing. This is not even a biofilm. Even in the non-biofilm format, they don't grow. Now I have numerous examples, but I realize this will be a video that will be circulated, so we can only sort of show a limited amount of unpublished data. So this is one set of unpublished data. So this is another outbreak organism of Candida auris. There was a Candida auris outbreak not so long ago, so we got interested in Candida auris. Of course, our main program is on Candida albicans, which is a much more sort of a popular pathogenic yeast. But in this case, Candida auris, you see how with the WED alone, you have a zone of clearance next to the dressing. And when we put amphotericin B, this Candida auris that we had, we obtained from the Center for Disease Control in the United States, and it is amphotericin resistant. But the moment you put WED and amphotericin B, now they're instantly amphotericin sensitive, and you're seeing this wide margin of clearance that you see. And this is just two, we have data from over a dozen highly resistant, antibiotic resistant, I should say, organism, and they all respond. The conditions may be a little bit different, and those are all sort of unpublished data. Soon thereafter, we had this paper that came out. That's a very important, in my opinion, landmark paper that demonstrated that species independent. It's not just a particular species. Somebody may claim, oh, well, this was a particular bacteria that this other Nature paper studied, and maybe it's limited to that bacteria and other bacteria. It really doesn't matter. Not the case. And as we are studying more bacteria above and beyond what is reported in these other papers, we are coming to the conclusion that this is a widespread. When I say this, I mean the whole, if you may call electrophysiology of bacteria is something that is quite broad, and encompasses not only the bacterial kingdom, but seems now also the yeast kingdom, and now more recently from our initial work on the coronavirus, as I will discuss with you shortly, we also see now effects in the virus. So there was a coverage also in 2017 of this article, and that talked about how bacteria uses brain-like bursts of electricity to communicate, and this is a very important development. You know, one thing that draws me towards this is that in every so many years, we have a new antimicrobial resistant bug. And sort of not being a microbiologist myself and not being in the business of developing antibiotics, I have the luxury of thinking that, you know, how long are we going to make these antibiotics? We have this generation and that generation, and a few months later, a few years later, we have a bug that is resistant to that new antibiotic. So how long is so let's think of a plan B. So that's what actually drew us to this biophysical approach of infection management, and that is actually exactly what I'm going to share with you today. So with all those cell culture work and molecular mechanism work, the question for us was very important to ask, does it really work in the actual field setting? So of course you cannot take dangerous bugs and infect a human. That certainly you cannot do. But you can do that to large animals that are considered to be good preclinical models. And in this case, we had a porcine model of burn. So in this case, swines underwent a burn wound, a relatively large burn wound throughout their body. And they were then injected with these bacteria. And we were trying to see whether, of course, in the worst case scenario, what you would have is this bacteria would not only colonize the wound and cause severe wound pathology, but in some cases they would even cause sepsis of the animal, as you can well imagine, as also happens in humans. So in this case, what we did was we injected these bugs that we knew were highly pathogenic, and in one case, we immediately after injection, after a few minutes or a couple of hours, we dressed it with this electroceutical dressing. And in another case, we allowed the infection to establish for 7 days, so that it is well established. So the former model, we call that the prevention model, and the latter, where the infection is already established, we call that the therapeutic model. So in the case of the prevention model, we were able to demonstrate that if you have injected this and you have a standard of care dressing, say we take a silver dressing that is standard in the hospital. So we actually, our controls are not just some textile. It is actually a standard of control that we apply to our patients every day. So we actually use an antibiotic, dressing control that patients get every day. And so that's our control. Now, against that control, when we tested this electroceutical dressing, we were able to observe that the biofilm could not be established in the wounds where the electroceutical dressing was used. And in the ones that we had allowed the infection to establish over a period of 7 days, we were able to completely disrupt that biofilm and bring and rescue the tissue and recover the healing process and achieve 100% healing even when the infection was allowed to establish for 7 days. So that obviously encouraged us and led to the design of a clinical study, which thankfully now the U.S. Department of Defense has funded, and in collaboration with our colleagues within the U.S. Department of Defense, a clinical study has currently started. So with that said, and before going into the coronavirus part, I would like to play this summary video, if you will, that sort of summarizes, in broad strokes, the paradigm.
Microbes are essential to life on Earth. There are as many bacterial cells in and on our bodies as there are human cells. Most bacteria live symbiotically with humans, but when skin's protective barrier is breached, bacteria can enter and cause infection. If left unchecked by the immune system or antibiotics, bacteria can multiply, aggregate, and develop a biofilm for enhanced pathogenicity. A staggering 80% of chronic wound and surgical site infections are caused by bacteria sheltered within a biofilm. Bacteria commonly occur as free-floating planktonic microorganisms. When they invade a wound, they multiply rapidly to form aggregates. Using weak electrostatic interactions called van der Waals forces, they attach and adhere to the wound surface in a process known as electrostatic adhesion. Bacteria communicate through electrochemical signaling called quorum sensing that enables bacteria to sense the density of neighboring bacteria and instruct their activity. They secrete chemical messengers that communicate with other bacteria and are translated into genetic signals that alter their behavior. Simultaneously, electrical signaling is the result of ions released in waves from within bacteria. This ion wave coordinates bacterial metabolism, aiding in recruitment of neighboring bacteria and further transforming their behavior. When messaging between bacteria grows strong enough, they begin to behave as a coordinated aggregate. They signal each other to secrete an extracellular polymeric substance, or EPS, that creates a biofilm shield around the bacteria, making them less accessible to the immune system and antibiotics. As the biofilm structure grows and matures, it becomes more resistant to destruction, leading to prolonged wound inflammation and disrupted quality of healing. Bacteria in a biofilm aggregate move in different ways to infect new areas and settle deeper into tissues following debridement. The body's immune system, alone or in combination with the drug, can usually kill planktonic bacteria. This ability to mitigate infection is crucial for resolution of wound inflammation and healing progression. However, once bacteria form biofilm, they are protected from attack by most immune cells and antibiotics, making biofilm infections notoriously difficult to treat. Researchers recently found that application of an external electric field delivered by a wireless electroceutical dressing can both prevent bacteria from forming biofilm and disrupt an existing biofilm infection. Bacteria were able to sense the electric field from the device. In essence, this external electric field short-circuited bacteria's electrochemical signaling, disrupting their ability to form, sense, and carry out the interbacterial communications necessary for forming and maintaining biofilms. Additionally, it decreased adhesive forces between bacteria and the wound surface, disrupting their ability to attach to the surface, thus helping prevent secondary infection. With the biofilm structure dismantled, bacteria are more susceptible to immune system and antibiotic attack. Infection-associated wound inflammation can subside, and normal wound healing can proceed.
Thank you. And with that video, which I hope you were able to hear the audio of that, I moved to March 2020, when all of a sudden we were served with the notice to shelter in place, and essentially labs had to be wound down. And that was the first time, we are not a coronavirus or any virus laboratory. And we started looking at the structure of the virus, the coronavirus itself. And of course, this is an oversimplification of the structure, but for our purposes, is good enough. So the focus here is on the string that you see inside. the beaded string that you see inside, responsible for the replication and the spread of this virus, the infectivity of this virus. And here what we are seeing is the single-stranded RNA and the nucleocapsid. And what we came across, the literature, not our work, other people's work, is that the single-stranded RNA is negative in charge and the capsid is positive in charge, and the electrostatic forces between the two play an important role, potentially in attachment and replication. So that's where we got interested in seeing as to whether this virus would respond to an electroceutical intervention. So in the beginning, of course, we did not have access to the coronavirus. We had to seek USDA permit to get the virus of interest, in this case, the VR2384, from which I'll show you the data. And more recently, we also got the 229E coronavirus, and we are seeing similar trends in both viruses, thankfully. So based on about 6 weeks worth of work, we reported a preprint. The reason we wanted to report a preprint of the several hundred papers, over 400 papers that I have published. This is the first preprint of my life. I've never felt necessary to publish a preprint, but in this case, I wanted it out because things were going so badly all over the place. I thought if we could release this, there would be people that would take this and take it to the next level. So that was the primary purpose of releasing this. We are still finalizing. In about a couple of weeks from now, much more work has now been done, and a full publication is being submitted. So what we were reporting at the time, as you see, the submission date was the 14th of May, exactly about a month ago, and it is about a month in the public domain, and I see more than 15,000 views and large downloads and so on and so forth. Attention score is high. It looks like a lot of people are looking at it, and also I'm hoping that some of those people are also scientists who would now take this and take it to the next level of solution. What we were able to demonstrate here, and I'll come to the data shortly, is that if you consider the coronavirus as a nanoparticle, size-wise, it is a nanoparticle. And since the virus does not replicate outside the host, when you have it, for example, on a fabric, it is nothing but a nanoparticle. Now, at that point, are the properties of that nanoparticle of the virus affected by the fabric, electroceutical fabric? And if so, does that have a bearing on the infectivity of the virus? And the reason we ask that is because, healthcare professionals are constantly working with people that are heavily infected, trying to save them. So they are working in an environment that is loaded, with a lot of virus. So obviously, when they have this PPE, the personal protective equipment that are laden with this viable virus on the outside, when they're doffing them or taking off the mask, there's clearly a risk of infecting themselves and infecting others. So the goal here was to come up with an approach that would stop such a spread of infection. So when you take that viral particle, in this case the coronavirus, and you apply it to the fabric, then what we do is we retrieve the virus from the fabric. We retrieve it after 1 minute, we retrieve it after 5 minutes, we do that in various time points. And what we were able to see is that when you put the virus onto the fabric, of course, a fraction of them. So if you apply 10 to the power 5 particles, as we do, you are able to retrieve about 40% in a minute, and about 25% in about 5 minutes. And we retrieve that in a way that it retains infectivity, because of course, when you put that in the so-called sham fabric, which is the polyester without the electroceutical property, you should be able to have complete infectivity with that, which we do. So what you see here is that, of course, the coronavirus stock is high, and as you see there, it is about, as you see with the red bar, and then you have FE1, meaning the electroceutical fabric for 1 minute, and electroceutical fabric for 5 minutes is your FE5. And then we use nanosite to understand the size of the particles. Then we measure zeta potential to understand the electrokinetic property of the particle. And we also do cytopathic assays, a series of them, to see whether this virus still retains its infectivity, and if so, to what extent. So what you now see here is that classical in A applied particles, when you now see you have a peak at around, let me see, is it around 115 nanometers? You have a peak. And then you have a storm size, so basically it's pretty homogeneous, and you have a peak at 115, and that is quite expected with this, and then the base is somewhere in the 70s. So you have that range that is consistent with this form of coronavirus that we study. Now, when you put it on the fabric for a minute, that peak becomes shorter, meaning now you don't have any as many 150 nanometer particles. Those number goes down, and you see clearly what we would interpret as aggregation of these particles. Now, aggregations can be good in some cases with respect to infectivity, and it could be bad in some cases. So that's something else. Infectivity is still not related to aggregation, but here you see aggregation. That's all you see. Clearly, there is an effect of the fabric on the virus itself. You don't see that with the sham fabric. In 5 minutes, that 115 peak 150 nanometer peak goes even shorter. So you clearly are seeing a morphometric difference in the nanoparticle as more time passes with the virus being attached to the fabric. Now, if you take this particle and these viral particles and you measure the zeta potential, as you know, zeta potential is a measure of the electrokinetic potential of the nanoparticle, and any of us that work in nanoparticle are used to measuring zeta potential all the time. So all this equipment, because we are deep into nanosciences, so that was all standard in the laboratory. So what you see here is that the zeta potential, as we report in the paper, is roughly about say around 30 or so, 25 to 30 millivolts, and it drops to about a half and becomes about 15 millivolts or so, and that happens pretty rapidly. So as you know, the zeta potential, regardless of the minus or plus, it's like a modulus. As you approach the zero, this means instability of the particle. So we thought that this could be a change in the positive direction. So you see the shifts of zeta potential, and the green in this case would be the virus that has been exposed to the fabric for 5 minutes. The blue would be the virus exposed to the fabric for 1 minute, and the red is a distribution of the zeta potential in the resting state. When you now take these viruses that come out, so if we look at A, B, C, D, I know it's a crowded frame, but A, B, C, D sort of separately. A, here there is no virus. All you have is the cell, and the cell, by the way, it comes as a match from the ADCC and is optimized for viral infection. So this pairing of the virus and the cell is an ATCC decision, and we stuck with that decision because our goal was not to reinvent the wheel, but just to test the infectivity of the viral particle. So what you see here is the phase contrast image, and then when you, in green, you see the viable cells, in red, you see the non-viable cells. So of course, in the resting cell culture, you will have some non-viable cells, but those are very few, and as shown by the few dots as you see here. And when you go to B, there what you see are cells that have been virus that have been actually stock virus, did not see any fabric, and it causes cytopathic effects as seen by the red. So you see cytopathic effects of the stock virus in B. When you come to C, you now have the sham fabric that does not have the electroceutical properties, and you see something that is comparable to B. You still are able to see those cytopathic effects. But in the case of D, even when the virus in this case was with the fabric for 1 minute, you do not see any cytopathic effect above and beyond what you already saw in A, which in standard cell culture, as we already know, there's a very small percentage of cells that are non-viable, and that's quite expected. Now, if one takes plots those data that you just saw, that's in A, and you clearly see that exactly what you saw in the image is exactly what is held. Each dot is data from a separate experiment, so we kept on repeating it until we were confident to report. So that's that. And in B, we went ahead and did another assay, a very standard assay, the MTT assay for cell viability. And in this case, you see in the untreated, you have a high cell viability. So higher the bar is higher the cell viability. And in the coronavirus group, you have serious loss of cell viability. In the fabric sham 1 minute group, you have serious loss of cell viability. However, in the fabric electroceutical 1 minute, we do not have loss of cell viability, and the same is the case for exposure to the fabric for 5 minutes. In this case, I would remind you that the viral load that we were using or that we were studying is 10 to the power 4. And so essentially what went into the fabric was 10 to the power 5, but then we got either 4 times 10 to the power 4 or 2.5 times 10 to the power 4 log in the log scale. It is still 10 to the power 4, so I call that a 10 to the power 4 burden. Now, interestingly, before we close this, I'd like to also point out that we have now tested a few other viruses, and I do not show you data from the gibbon ape leukemia virus, which is used in viral laboratories, especially viral gene therapy laboratories, pretty common because of its high infectivity. The gibbon ape leukemia virus, we could completely block its infectivity. And here I show you data from a lentivirus also used for viral gene delivery. And you see we can wipe off the infectivity of the lentivirus once you have shown it to the fabric, in this case, for about a minute. With that, the take-home message here that we have so far in this unfolding story is that the exposure of coronavirus to a fabric with electric field changes particle size, changes the electrokinetic potential approaching zero, indicative of destability of the particle, and causes loss of infectivity. And the broader message out of this is that this observation encourages the consideration of electroceutical approaches, not just in antiviral or antibacterial drugs. They have their own place, but this is a different modality, call it a plan B, to limit the spread of infection. With that said, I'd like to thank our key sponsors, the National Institutes of Health within the United States, as well as the Department of Defense that fund our laboratories. And I sort of went through numerous studies, so I don't have the opportunity here to name every single person. Therefore, credit to all the authors. They're appropriately named in all the publications. And I also have my website displayed here. Thank you very much for your attention. I'd be happy to take questions.
Thank you so much, Dr. Sain, for that wonderful talk. We have a few questions submitted through our Google form. First question was, have there been any studies with respect to the safety of electroceutical fabric applied to the human skin?
Yes, there has been. And so the fabric that you now see, which is the source vomaris, that is already FDA cleared and has been used in patients, I don't know exactly how long, but at least 5 years, I would say. So, and no safety concerns have been reported so far as I know. So far, it is being used as, certainly not as a mask, but as a wound care dressing. I hope that answers. And the second part of it is the other fabric that I discussed about, which is the 6-volt fabric. We just published a paper with testing on patients to show that it is also safe. Even the 6-volt one is safe, and the lower one, which we call the wireless electroceutical dressing, both have proven safety record.
Along those same lines, do you think such a mask is economically viable in providing protection to the general public? And people are also asking, when can we expect these masks to be commercially available?
Yeah, I see. When I was answering the question, the CEO of the company is texting me. So it looks like the company is online, but maybe they're not in a position to speak. This is purely, so all I can tell you is that we have had a meeting with the FDA, and they have sent back a few questions. And this is in the commercialization space, is all up to the company. Of course, I'm associated with the company, but that is the question that you're asking is purely commercial in nature. And of course, the company is doing this to take it forward very fast. But I would, not knowing exactly what the manufacturing cost is, I would rate the cost to be relatively low because you don't have any sophisticated electronics here. You're talking about printing certain. Of course, there are proprietary manufacturing steps towards that will have some cost, but it should be very affordable based on my understanding of the manufacturing of this type of fabric.
In terms of the safety of such a mask, a lot of people are using these regular cloth masks. So is there a clear difference in transmission and infectivity that you've seen?
So the key issue there is, let's take the standard N95 mask as a reference. The N95 mask uses a filtration principle. so it will not let the particle in, and therefore we are protected. But we see there are two important points here. First, N95 is not available in abundance, and in many cases, N95 needs to be reused. But if the exterior of the N95 is contaminated by viable virus, its reusability is limited. So if one can combine the two with having the power of the filtration, but the external surface of that mask would have an electroceutical surface, that I think would be an ideal. Now, whether it is achievable in the short run, that's another practical question. But from a principle standpoint, I would view that to be the most appropriate sort of approach.
Another question we had submitted was, as viruses have different properties from bacteria, are there modifications that must be made to the electroceutical fabric to target viruses compared to the original application for biofilms?
No, that is the beauty of this. So we seem to be in a sweet spot where, just a little bit of in rewinding, just to get to the context. You see, where we have seen limitation of the fabric is when you have a deep tissue infection and the electric field is not good enough to access that. And that was the motivation for us to develop what we call the PED, the patterned electroceutical dressing that actually gives you a 6-volt and is sort of conventional battery powered. In this case, you don't have that issue. You don't have any depth issue. So it looks like that what you have in the WED, the wireless electroceutical dressing, is appropriate for the bacteria as well as for the virus, no tweaking needed, based on the current data that we have.
And in terms of encountering viruses, if very high viral loads were encountered, would the electroceutical fabric still be able to prevent viral infectivity with the same efficacy as you've reported?
Oh, very good questions. Thanks for asking that, whoever asked that. So you will notice that all the data that we have so far shown uses 10 to the power 4. That's very high, 10,000, you know. And now the experiments that we are doing with the human coronavirus, we actually have taken it all the way to 10 to the power 6, 2 orders of magnitude. That's really high, okay? So even there, we see complete protection. It's just a matter of a different time interval that it takes to be inactivated. So given that we are seeing favorable data with 10 to the power 4, as well as with 10 to the power 6, I think that covers all those bases about the dosing of the viral load, I should say.
Along those lines, is the antiviral effect of these masks, is it reversible?
Another very good question. You know, I'm sure you have a lot of bench researchers in your audience. So it is not reversible because what we do, if you recall my experimental design, we applied the virus to the fabric. We retrieved it off the fabric. So our infectivity measurement was not when the fabric was in position. It was when the fabric was withdrawn. And then the virus had 7 days to infect. And in all those 7 days, it couldn't. So therefore, based on that, I would say it is not reversible. Had the fabric been in place while we are studying infectivity, reversibility would be a question. But because we're having this 1-minute exposure, retrieving these viral particles, and now using that to infect cells for 7 days, and you don't see infection, I think that conclusively shows that it is irreversible.
And one final question we had, I guess a multi-part question. Considering that this will be more expensive than a regular mask, to reuse this needs to be washed between uses. Are there any specific detergents that can harm the electrical potential or should be avoided? And also, do you need the mask to be moist to be active?
Two, again, very good questions. So first, it can be reused. And you know, when you put metals, and this is company information, I'll give you my understanding, and I will not get into anything proprietary. So when you put metals on fabric, you use something called binder chemistry. So the binder chemistry of this particular WED, as far as I understand, is ratified for several cycles of machine washing. And it shouldn't be a problem to have, I mean, home, I have used it with home, you know, detergents, and it should be fine. But of course, after a particular cycle, I cannot say exactly how many, I believe it is anywhere between 10 to 12 cycles, you will see degradation and erosion of those metal deposition, at which time the yield of power will fall. And the second part of the question was? Does it have to be moist? Yeah, I got the question.
Yes.
Does it have to be moist? Yeah, so the construct of this will have to be such that you have these, you have the fabric in the middle, and you have a frame that has these conduits that will contain liquids. And through wicking action, it will keep the fabric moist. So it doesn't have to be dripping moist. It just has to be moist. So it's just a matter of how you formulate the mask itself.
Great. With that, I'd like to thank you, Dr. Sen, for taking the time to do a presentation for us today. We really appreciate it. For everyone else, the recorded lecture will be available on our Center for Personalized Medicine YouTube channel. So please feel free to share. We'd like to thank our sponsors, the Wellcome Center for Human Genetics, St. Anne's College, and the Center for Personalized Medicine for their support today. And we hope to see you all at our upcoming webinar this Friday. Thank you all for attending. Thank you.
Thank you all. Thank you.